Thanks, everyone. Today I'm talking about basically the design and how you run low latency systems. It's really awesome that the talk right before this was also about low latency, whereas the previous talk was kind of a very much so a deep dive and an implementation of one particular aspect of low latency. I'm going to try to kind of prescribe things in the general case that you use to build low latency systems, regardless of what the domain is. And then how you would actually go about running them. So this talk is kind of in two different sections. The first section is the design of the systems generally and kind of the principles you use to design these systems. And then the second half is basically like the practicality and like features that you would need to actually run that in a cloud environment, specifically on Kubernetes. So I'm Jimmy Zelinskie. Thanks for the introduction. But if you're not familiar with me, I'm kind of someone that's been in the cloud native ecosystem for a super long time, literally the beginning. So I started a company called AuthZ, who builds a product called SpiceDB. I'll get into that later. But I basically was working at Red Hat before that via the CoreOS acquisition. So I basically worked at the company that created the idea of Kubernetes operators, which is basically teaching Kubernetes how to run software programmatically, like a human would be an operator for a software running on a cluster. Before that, I worked on container registries. So my co-founders actually created the first private Docker registry before Docker even let you store private images. And then I'm also on the container standards body from that work. So I actually maintain the specification that defines exactly what an application container is. And then I've also worked in the BitTorrent ecosystem for a while, and I've also authored a couple of the specifications there. But I actually wrote BitTorrent technology that, while I was in college, I just thought that was fun. But then it ultimately became the thing that actually distributes containers at Meta on all of their servers. So be careful what you build. People will use it in very unexpected ways. Cool. So I feel like you can't talk about low latency without jumping in and kind of like level setting what low latency means. Because there's a lot of different contexts. There's a lot of different latencies, right? If you're building front-end UI components, like the latency for a human interaction is not the same window of time that you'd be talking about if you were designing maybe real-time embedded systems or like an airplane controller, right? So how low are we talking in this talk? I'm basically going to be talking about something that could be a network service, something in like the single-digit milliseconds. Or potentially, if you were to totally cut out a network, would be less than a millisecond. So I'm not talking about like hard real-time or soft time. I kind of have these images to kind of make it more intuitive. I'm not talking about the thing you would do if you were writing the software on a pacemaker, right? That thing has to be way, way, way more real-time. Someone's life is in your hands, literally. But I am talking about things that could be like doing trading on a financial market. And so just to like make it a little bit more concrete, you can use a garbage collected language for this. And you can run this type of workload in the cloud. So SpiceDB is kind of the project that has kind of guided us through this process. We've learned from building this software. And that's kind of what my talk is designed around. So I'm going to use examples from building SpiceDB. So if you're not familiar with a permissions database, which you probably aren't because we're kind of pioneering this topic, a permissions database is a database system that is specifically tailored for storing authorization data. So this is the data that you're using to grant access to perform operations in your application suites. There's a lot of guarantees and nice properties when you take this out of code that you have scattered across your product portfolio and centralize it into one place. When you put it in that one place, you can start to basically reason about the system external to your own code as well, like your own systems. So we can basically give you a schema language, and you can test that schema with data in a vacuum and make changes to it outside of any of the code in your application. This is really cool, but it also comes with very interesting requirements around the performance of the overall system because you need to be able to scale for arbitrary amounts of data. For example, all the data stored across the G Suite, like product suite. So everything in Google Docs, everything in Google Photos, all these things all combined together. And then you also need to be able to have that be globally deployed, but also consistent, because if you serve data, if you give a response for a permissions question, and it's not consistent, that's a vulnerability. You've given access to someone that maybe they shouldn't have had access, but you gave them a stale response. So this is some really, really interesting distributed systems problems for you to solve. And just like for some perspective, the criticality of the system also is really important, because this is before you ever talk to your relational database. Like a request comes in, you have to do this check first. And then you get to decide, OK, yes or no, they do have access. Now I can reach out to the relational database. So even the latency on relational databases, probably higher than what you have to pay for this. So SpiceDB is actually inspired by a system that's used in production at Google. This is actually what is serving all of the traffic across G Suite when it comes to permissions. It's the cool thing that powers like basically asking questions across their product suite. So if you send someone a Google Doc link in Gmail as an email, it'll pop up a warning, because Gmail can actually check the central database to see if you've granted access already to the Google Doc. So you get all kinds of really interesting behavior that you wouldn't otherwise get if you didn't centralize all this stuff. But basically, Google scale is huge, right? And in the paper they talk about theirs, they talk about 20 million QPS. We tried to benchmark SpiceDB to try to get somewhere similar to that number. We ended up running out of IP addresses in Google Cloud. This is what always happens when you try to do big scale tests. But when we did measure it, we put 100 billion rows, that's billion with a B, inside of our database, and we ran it at 1 million QPS, and we basically got 5 milliseconds at the P95. So this was about a year and a half ago. These numbers are probably better now. Bless you. Cool. So how do you design for this type of low latency? Well, I say this kind of jokingly. The thing is, you write it as simple and understandable as possible, and then you just profile the hell out of it. If you're not familiar, profiling is when you actually sample production systems and look at where time is being spent. You can measure this. You can use this to measure basically CPU. You can measure allocations in memory. But kind of my philosophy here is largely around making sure everything is understandable and correct first, and then only then do you actually start measuring the system and understanding the system. And there's kind of this loop that you will always go through where you're going to make a hypothesis, and then you're going to test that hypothesis, and then you're going to, once you test it, then you're going to profile it, because then you need to make sure that your hypothesis, even after you've tested it, holds true in a real-world scenario. And I don't think there's really any other way you can build these systems without following that strategy over and over and over again. Because if you design it in a vacuum or using pure computer science concepts, the real world is going to smack you in the face. And there's kind of these two types of profiles that are the most useful that you're going to get. Concurrency ones and memory ones. And I think they're the most convenient ones because they're both these convenient lies that the computer is telling you. The concurrency lie is the computer lying to you saying that a single core can do more than one thing, right? It is telling you that, hey, I can actually run two things when actually it's swapping between them very quickly. It's a useful abstraction, but it is a lie nonetheless. The other lie for memory is your garbage collector. It tells you you have infinite memory, right? Because it's just going to clean up after you make all of your allocations. This is very convenient because you don't have to litter your code with manual memory management, but it is still a lie. That still is operating underneath you. You need to understand that system. So on the concurrency control, you have literally your language runtime that is providing you something, or maybe the operating system if you're calling into C libraries to just get threads directly. SpiceDB is written in Go, so I'm going to kind of frame things around Go. Go has its own scheduler where it is running Go routines for you. That's really, really cool, and it gives you a nice abstraction. But I promise you, if you build a system where you're just randomly calling Go to run Go routines, you're going to build a mess. Because it's not going to be aware of your workload. You're not going to set limits on any of those things. You're not going to be able to cancel things. You will not keep track of all of that work that's being done. So you actually have to work with the runtime to build another higher level abstraction around all this stuff. So you can set limits, cancel things, prioritize things. Because if you just fire off Go routines, maybe a whole bunch of super low priority things block progress on something that's hypercritical. And the scheduler in the language does not give you any handle into actually teaching it what those things are, so you have to build those abstractions yourself. On the memory side, it's kind of a similar story, but this is about allocation and garbage collection. So I followed the opinion, and this is definitely probably a hot take. I think for this type of application, you can use a garbage collected language. Like, you absolutely can. And I think the benefit of doing so is that the vast majority of the code that isn't performance critical, you can write and understand in the most obvious way. But then, only then, do you sprinkle on the parts that are critical, additional logic and complexity, so that you can get the performance you need. So as long as you have some handle to controlling the allocation in your garbage collected language, I think that it's viable in this scenario. And obviously, we picked Go, so we're biased on that. But then the other nice thing you can do with the GC is kind of like tune it for the workload, or a lot of GCs come with different knobs. And as long as you have access to control those, things like being able to understand if your GC can handle very short-lived objects, if it's generational or not, for example, super, super important to understand when you start building these things. So kind of on the first route, the best thing you can possibly do for concurrency is try to parallelize everything. That if your problem is inherently parallelizable, that's what you just have to do. Break it down and try to do as much as possible across a bunch of different cores. Because CPUs aren't getting faster. They're just getting more dense. So SpiceDB is actually Kubernetes aware and self-clusters. So not only are we kind of breaking up work across Go routines in a single process, we're also doing it the next level up, which is clustering. So we're actually spreading work across a whole cluster. So when a request comes in, we can actually break that request, the computations that have to be done, into a tree. And then the expressions are then dispatched across the entire cluster. That's super useful, and we use a consistent hash string to do that. And then you can actually cache that. The really interesting thing with doing it structurally is if there are two different requests, but they share a structural computation as an intermediary to computing that, that gets reused. So if you have a caching system that's aware of the computations actually caching the computations, you can kind of think of it like a thunk more so than like a request cache. So I already covered the kind of scheduling the task by priority. That's also just done by abstractions. And there's kind of two things that are, I would say, critical in every language. If you don't have these libraries written yet, you should write it. And that's single flight, which is the idea of like function called deduplication. Basically, if one request comes in, you start serving that. If another request comes in for the exact same thing, you basically wait for the first one to return, and then you give the response to both of them. This is super, super powerful. It's incredibly powerful. And once you have a good abstraction for it, you just start sprinkling it everywhere, and the latency just drops. On the other side to that, there's hedging. And so hedging is when you basically do the same request, but you ask two different people. Because if something bad happens to the first guy, you can't actually spend the time to wait for that timeout to trigger and then ask again or ask the next guy. So you just ask the next guy immediately. This is kind of like a double-edged sword too, though, because if you hedge, you're putting more workload on your overall cluster. So now you probably have to scale up when you would have previously before. And just in general, like that has trickling effects because it's not just across your cluster, it's across your abstractions that you built around concurrency. It's everywhere. So this is one of those places where you have to really, really measure to see if hedging is working for you. And it might in one part of your code base and not in another. So always, always test these hypotheses, except for maybe single flight. That one probably just always works. Cool. Then on the memory side, basically, you're not going to ever want to use disk. You want to get everything into memory. Obviously, for consistency reasons, like things are going to eventually hit disk at some point. But you want to keep as much in memory as possible. And that means you might actually have to write some of your core data structures. We were super lucky that basically TinyLFU, which is the caching strategy we use in SpiceDB, was already written in Go by the dgraph folks in a library called Ristretto. It's fantastic. We've been able to basically push some changes and patches and help maintain that. But if you don't have something like that, the thing that you need in your language, you're implementing it. Like, it is the core part of your whole application. Data structures define your applications. And when you can't actually serve your traffic from the data structure you built, the next thing, the fallback, that thing better be ready. Like, it has to be perfectly capable of serving that request in the minimum possible way. And I'll give you a concrete example. I use connection pooling here. The pools of connections in SpiceDB, when you do have to reach out over a connection, it's not just a pool where you're kind of returning stuff to a pool. It is always full. That means I take a connection from the pool and I immediately replace it in the pool. I need to know that there's going to be connections always in the pool, because establishing a new connection and a TLS handshake, that's enough to blow your SLA when you're trying to do like single-digit milliseconds. So that's just like a concrete example of that. There are a lot of places in your code base where, hey, if I fail over, like, you have to be ready, basically already maybe working on it, hedging against the cache miss. I mentioned earlier kind of GC pressure, like making sure your GC is aware of the environment it's in. Basically, if you are deploying this in an environment that has X gigs of memory, like, the GC needs to know that, because it's going to do all kinds of different things with that information. Like, if it thinks it has 2 gigs of memory and it really has 100, you're going to be struggling with GC pressure when you absolutely should not be. And that's all, like, the GC is basically trading like throughput for latency. Then reusing buffers is probably the fastest way you can speed up any code, like, on the internet. So if you're not already like using things like a pool to reuse allocations for the data structures you have already allocated on the heap, you're going to start doing that everywhere. And then not only that, once you've done that in your critical path, you're going to go to your dependencies and look at all the libraries in the ecosystem and start sending out PRs. A great way to get a good reputation in your library like ecosystem is to start opening these PRs, because sometimes it's really simple. A lot of the times it's hard, but sometimes it's really simple. And when you add this, like, really simple small PR that just so happens to like 100x the performance of a library, people like those PRs because it affects everyone who's importing that library, right? And then kind of finally on the memory side, if you use simple types, that is going to benefit you kind of in 2 different ways. The GC, if you have, for example, a hash map in your programming language, and you put integers inside of it rather than pointers, the GC can look at the type and say, there's no pointers to follow inside this map, so I can skip the whole thing. And that whole thing could be gigabytes on your heap. But if you have pointers in there, it means it has to iterate over every item in the hash map to follow all those pointers. So you get a huge benefit out of kind of using simple types. You might be surprised where you could use some sophisticated computer science to come up with a better thing, but in actuality, using the real dumb thing just goes fast because processors are simple. So that's definitely a thing, but also the processors are simple. So when you don't reach into the heap really often, you can actually cache the stuff in the CPU cache. So it's not going to invalidate a cache line trying to follow some pointers from memory. So you kind of get benefits even on the CPU side, although that's probably not going to be your bottleneck when you're kind of developing these systems, unless you're really number crunching stuff. In that case, you're probably using crazy vector instructions to make things go fast. Cool. So now you've designed a system that's using all these tricks. It's going really fast. How do you make sure that your environment is actually going to be able to run this thing and run it in a way that it's going to perform its best? So for context, all of our products, our SaaS products that we sell, they're basically managed SpiceDB running on Kubernetes in the different cloud providers. But it wasn't really our first time using Kubernetes. Kind of like if you paid attention for my bio, I've been here since the beginning. I've been building Kubernetes. I was a product manager on Kubernetes at multiple companies, and I've built core parts of it. Our team are all experts in Kubernetes. We've built basically chunks of it. And it still wasn't easy for us to figure out how to run low latency workloads on this. So it's not exactly what you think. But you got to start somewhere. So in the beginning, you just kind of put it on the cluster, and you use the defaults. I like to think of the Kubernetes defaults like your Linksys router, right? Like there's like a password that comes. Sometimes it used to be like admin, but now at least it's a random string that they just put on a sticker. And like I'm sure if I like clicked on my Wi-Fi right now and you saw the giant list of all the APs here, you'd see all the default names, and you'd know no one actually changed that. It does work, right? Because like those APs are in the list, right? You can see them. But it's not really the best thing you can do. And so in the Kubernetes defaults, it doesn't actually protect you from basically consuming any of the resources on the node. So if another pod, which is the kind of unit of execution in Kubernetes, gets scheduled on the same machine as you, it can consume all the memory. It can just completely tank your system, and it's just a noisy neighbor. And so like that's a huge issue, but then also Kubernetes scheduling is also best effort. So if you have 3 replicas you're trying to deploy, but you only have 2 nodes available, maybe like one of the nodes is just, maybe you have more than that, but they actually just have stuff scheduled on them. It's going to schedule 2 of your workloads on the same machine. If you're trying to give your customers guarantees of HA, like that's not great. That machine gets broken, or like maybe it's a spot instance on Amazon, and Amazon's like, your time's up, kill this machine. Now you've just dropped down to a single replica. Depending on your workload, if it's something that needs consensus, oof, like you just killed your cluster, you're screwed. So special attention needs to be taken. So what can we tell the scheduler to pay more attention? So basically, there's this general concept called affinity and anti-affinity, and that's kind of like basic rules around what things can go where. These get facilitated in Kubernetes by a feature called taints and tolerations. A taint basically says this particular workload can only run on things that can tolerate it. And then the different machines, you give tolerations to say, this machine can tolerate things with this taint. So it kind of like does matching across them. You can use this abstraction to basically give you guarantees like, only run 1 pod of this kind on this machine. And if you get really clever with it, you can basically create a whole new work pool of nodes and then have it so your particular workload only gets scheduled on that hardware. So now you can start to choose what specialized hardware your software is actually getting deployed to. Super, super useful, especially because you probably have a bunch of like extra shit running on your cluster, like things like Prometheus monitoring it, your alert manager paging you, right? You have like logging, all these things. Profiling, if you've been paying attention. So basically, you do want your low latency workloads completely separate on a different type of hardware. And then this is kind of the basic advice you get. If you just Google this, like you're going to get requests and limits. People are going to tell you, oh, Kubernetes supports this. Just add requests and limits onto your thing. So you can specify this workload. It needs approximately this much space. And then at a hard limit, you should only ever allow it to grow this much. And at least this buys you something. Basically, yeah, we're done, right? That's it. You just add that and you're good. This does buy you a decent amount. You're not going to get killed by the kernel. Like before, the kernel is going to be the one to decide who gets killed because it's just seeing processes eating memory. At least in this scenario, Kubernetes now knows what you're doing. And when it sees something pass that threshold, like of the limit that you set, it's going to kill it. So Kubernetes is going to be the one to kill it, not the kernel choosing a random process. Great, we made some progress there. But you've also basically made the performance more predictable by saying, OK, everything gets this specific amount of hardware by doing that. The kind of downside to this is you actually lost a benefit that you had before that was kind of a blessing in disguise. Before, you could have burst on that node, right? Like if the other process is running there, maybe it's like a logging driver or something. It's just sitting there. It's not doing much at all. It's not actually consuming all the resources it probably should have reserved to it. You could have bursted before to consume some of those resources. That's a really nice property, actually, but you kind of lost that. It's a double-edged sword, though, right? Because they can burst and hurt your latency critical workload, too. The other thing is kind of an implementation detail, and most people don't realize. The limits in Kubernetes are actually reactive, not proactive. So there is a polling rate that is configurable in the API server. And it just sits there, and every so often it checks in to see, have you exceeded your threshold? That check-in, it's not low latency, right? Like if your window is, I'm serving let's pick a very small number, like 100 requests per second, right? But it's checking at a rate less than that. That means something can burst past you still, even though you've set these limits, enough to tank a whole bunch of requests and like basically disrupt your workload. And then your pods, we're also sharing the same machine. They're still noisy neighbors and stuff. So you're going to suffer from context switching, which, if you're not familiar with context switching, I'm going to do a quick kind of interlude into that. Context switching is all part of this kind of concurrency lie that I told you about earlier. So the difference between parallelism and concurrency is basically in parallelism, you have two different processes and they're running completely independently. They get full time scheduled to execute. In concurrency, you actually only have one thing that can do work. So what it's going to do is it's going to basically run a workload, then it's going to stop that workload. And how it decides to stop is kind of two different types of what we call scheduling. There's cooperative, which is an event triggers it, or there's preemptive, which is I just decided right now you've been running for too long, so I'm going to stop you. And then it stops that workload, and it restores the state of another workload and then starts executing that, and then it does basically the exact same thing again in reverse when it decides to switch to another workload. There's some scheduling overhead here, and obviously this is expensive in terms of like CPU time, like your workload isn't running in all that time. But the kind of interesting thing here is I say there's kernel scheduling overhead, but actually there's a bunch of different layers of this scheduling happening in your program. Go, the programming language, has a runtime. It's running your Go routine. It has a scheduler. It's context switching across threads that it's basically assigned to your process. And then you have Linux, the operating system, doing the same thing with processes, context switching. And then you have your CPU. Does it have hyperthreading? Hyperthreading is also context switching. You're sharing a single core across two hardware threads. So you're getting layers and layers of the scheduling that you need to work with and basically try to simplify as much as possible to make it closer towards this parallelism thing where you get the illusion that two things are just running. So how do we deal with this context switching? And Kubernetes has one last trick up its sleeve. And this is a feature that not many people know about, which is called the static CPU manager. This is introduced in 126, which is probably in the release available to you now, because I think they're shipping 130 right now. So it's almost certainly what you're already running. And what this lets you do is if you set this policy to be enabled and you give a pod a whole integer number of cores, it is going to guarantee that that runs dedicated on those cores. So you're pinning cores to your process. So now you don't have to worry about other processes doing that, like basically taking over any of the CPU runtime that you have for your application that you're running. That's great. There is one slight caveat, which is what about the rest of the stuff running on that machine? You do have to save one core left for that. So there is like some cost overhead to doing this because you're effectively wasting one of the cores on the machine, quote unquote wasting. But that's static, right? So what happens if we need to scale or like things change, we want more cores than what we've just statically defined? That's where auto-scaling for Kubernetes comes in. We use this project called Carpenter. It was originally started by AWS, but now it's a CNCF project, so it's actually totally neutral. And that's because Azure actually replaced their proprietary autoscaler with Carpenter support. I'm hoping Google will do the same eventually. Right now, Google has their own proprietary one called Autopilot. You can use that. We use that on GCP. But Carpenter is kind of the nice neutral one. And what Carpenter does is when you go to schedule a new pod, it will actually talk to a cloud provider and spin up a new VM specifically for that pod. So it waits until the scheduler says, hey, there's no room, and then actually makes the action to go and provision you a new machine that you can run this stuff on. So that kind of like adds back the dynamic aspect that you lost when you made everything static. So to kind of summarize at a very high level, if there's one thing I want you to take away from this talk, because I talked about a lot of different like small concrete pieces, but the overarching theme, if you like squint at all these things, is that basically isolation is the only way you can actually guarantee that something is going to run with consistent latency. And not only can you just like isolate different components and keep them blind, they need to be transparently aware of the context in which they're running. So for example, the garbage collector needs to be aware of the environment, the memory that you've provided the environment. So basically at the top level, you have the hardware limit that you've configured in Kubernetes. Then you have the garbage collector that needs to know that. But then you also need to know in your application code what the garbage collector is doing so that you can also manage the garbage collector. And like, you need all these things to be isolated, but they also need to be aware of everything else that's happening, but not modify the things. That's kind of like what gives you the isolation. So I think isolation models are super, super important, enough that they're in our documentation for SpiceDB, and we use them in product marketing for our database. Like, I think that a good product, and we've designed our product around having isolation. I just think you need it to actually effectively deal with these workloads. So surprise, I'm actually a product manager. I'm not a software engineer, although I have been, and I do carry a pager. So yeah, but I'm actually chief product officer for our company. So I'm actually in the product space. This hasn't been a product pitch, but I want you to believe that isolation is super important when you start evaluating other products as well. So I'd like to give a couple shout outs. Folks at AZ that kind of contributed to a bunch of this work that we kind of like discovered. If there is one external resource that you look at for understanding at least the Kubernetes primitives available to you, that's this Medium link, which that's as short as I could get it, sorry. But that just runs through the different things that you can configure in Kubernetes at like a level of detail that I was not able to provide in the talk. I wanted to thank the hosts for Trail of Bits and Phil for organizing. If you want to talk to me ever, I have my email here. It's jimmy@alsed.com. And then also we run a SpiceDB Discord. This is purely about like SpiceDB community stuff. So if you're interested in kind of Go and distributed systems and databases, that is the place to talk about that. Also, we're hiring. We're hiring engineering managers and SREs. So if you're interested in running these types of workloads, feel free to reach out as well. Just send me an email. Cool. Okay. Thanks, everyone. We have time for questions? Cool. Sure.
Do you access distro with SpiceDB? And I wonder how you made that low latency as well.
Yep. So the question was, do we access disk at all for SpiceDB? The answer to this is actually probably more complicated than you think. SpiceDB does access disk, but how we actually do it is we have a data store interface that is actually pluggable. And we actually plug into other databases as well. So you can actually choose kind of like your storage layer. For example, if you wanted to run across the whole world, completely geo-distributed, we actually will use CockroachDB in that scenario. And so then we're actually kind of like a meta layer, the same way that you would basically have like RocksDB below your database. We implement our data storage drivers on top of other databases, so we can kind of like leverage some of their properties as well. And honestly, it's really hard to introduce a new database product like managed. So if people want to run something, they probably want to point it at like RDS or something that already exists. But we also do have like in-memory implementations if you're doing like peer testing. But also, there's no reason why you can't take our data store interface and just implement something that just does it with RocksDB or SQLite or anything like that. So we do eventually hit disk. But like I said, the goal of the project is to serve everything as much from memory. So in SpiceDB, we basically do that by only querying for relationships when we absolutely have to, like we haven't loaded already into the cache. There's a lot of different configurations for you to basically avoid hitting the cache or like prefetch things as well. But we also then have another project that is more similar to some of the concepts that were being described in the previous talk, which we call Materialize, which is a giant materialized view. Basically, it follows the changes going into the database and builds an in-memory representation of that. So that one will always be up to date. And the layer that I was kind of showing before where you dispatch to other nodes, you can actually dispatch to that to read directly from the pre-materialized view. And in that scenario, everything is always in memory, and you're always serving from memory. You're never hitting disk. Yeah. Cool.
You mentioned using buffers for as a performance optimization.
Yep.
How often do you find yourself maybe thinking about the size of cache lines and your page size, or making alignment, like the lower level node and stuff?
Yeah, I think, so okay, so the question was, I talked about reusing buffers and things, basically allocation focused. How often do I find myself thinking about the actual cache lines and like the implications of basically like blowing the cache on the CPU rather than the kind of higher level things? Very infrequently, I would say. I think it really matters in hotspots, and this is why profiling is super important. I think it depends on your domain. For our domain, it's really more about kind of like graph traversals. Fundamentally, at the core, we are a graph database. So we're actually doing a lot of like recursive pointer chasing is kind of like the implementation details. But if you were doing something else, I could definitely see a world where like you're definitely like deep into it and like measuring basically the time you're spent in per cycle. But yeah, this is one of those things where I'm like, you just gotta listen to the profiler. You run the profiler. If it's telling you you're spending all your time like doing some number crunching, like that's what you're gonna be optimizing, right? Cool. I saw another question over here. Yep.
I was curious, how do you come up with SLAs when you're building a product on top of the cloud?
Yeah.
Like, let's say there's like an AWS EVS stall. How do you communicate with the customer that is the cloud provider's fault and not yours?
Yeah. Okay, so the question was, if you're building a low latency product and you're basically dependent on a cloud, how do you come up with SLAs when the cloud provider could be at fault, and how do you like communicate that to your customer who is then transitively dependent on that cloud? It's interesting because there's like, you're lucky I'm a founder. I get to see the contracts and things too. You actually do, it depends on your business. Often you'll actually write that into the contract that like these are the types of things you get an SLA on, and the cloud provider going down is not one of those things. It can be excluded. And that just depends on what the product you're selling to, because if someone really wants to survive the cloud provider going down, they probably should be deploying a like disaster recovery scenario. So like either active passive kind of failover to another region, or active active where you're actually like clustered globally. So if someone actually cares about that type of outage, that's when we would push them towards one of those environments instead. But yeah, there's always dependencies, and you try to minimize your dependencies as well, just fundamentally. But yeah, at the end of the day, like hedging is the other thing you can do too, is basically make sure that like if you're dependent on a service, you have some backup plan and that it's ready to go if that thing goes down.
So you were talking about how you were Cloudware, you tried to basically break up your queries into a graph of requests to other nodes.
Mm-hmm.
Each request increases latency quite a bit. Network is a lot slower than RAM.
Mm-hmm.
How do you trade off the trying to keep queries local to a node and therefore low latency versus not?
Yeah, that's a really good question. So the question was around the dispatching layer, which in SpiceDB, we break down requests recursively based on their structure, and then we dispatch that out to the cluster. So network hops are expensive. So you kind of have this decision where you're like, do I hop over the network to compute this? Is that going to be worth it, or should I just compute it locally? The way we've kind of worked around this is by having both a server-side cache and a client-side cache. And what I mean by that is when you make a request across to consistent hash, basically it picks this node, I'm going to dispatch to them, they're the one that should own it. I actually remember the answer they give back to me. So that way if someone else requests that, at least I have that already in my cache as well. So I'm caching kind of at two layers. The layer where like this guy is assigned, he's pre-computed this probably, it's in his cache, but also I talked to him recently. So I actually already know the answer to that question too. So you can kind of do this double layer caching to help alleviate some of that. But at the end of the day, at least in SpiceDB, we've basically just said that trade-off is worth it. Like basically being able to know how the data is layered on the cluster, like laid out on the cluster, is worth the network hops that you get. And you do all the tricks that you need to basically make those network hops as fast as possible. I'm actually kind of surprised by this. The dispatching layer actually isn't the slowest part. Like networking out to something, if you're using like an RDS backend, that actually hop to RDS is slower than what you're going to be doing internal to your cluster. So actually like the networking at the internal cluster layer is quick enough that we haven't actually really seen that be a problem for serving like single-digit milliseconds. Yeah. Yeah, so ends up being worth it basically. Probably the client-side cache may not even be super worth it, but honestly, like we don't have excessive cache usage because there's another aspect of SpiceDB where like permissions become less important over time. Basically, the freshness matters, so we're actually keeping track of freshness to do a whole bunch of consistency work, which means we can actually evict our cache over time. So we know after a certain point in time we can evict all that cache because it's so old no one cares about it anymore. There's actually a lot of parallels between the join problem and how we kind of like quantize and handle consistency in SpiceDB, but that's another talk. Yeah. Cool.
All right.
Cool. Thank you.
Thank you.